Hi folks, we're going to take a look at the solution to number 16 from page 129. So what they give us here is this position function, which is defined as a piecewise function. Now you might sort of wonder, why are they even assigning a value when t is less than 0. I think we'll see when we look at the question, because it looks like they're asking us to determine that the acceleration function is continuous. So again, if something is officially continuous, it has to have a limit, and you have to be able to approach from both sides. So presumably they're putting this in to sort of ensure that we can approach it from both sides. So that's what the first question is. It says, shows that the acceleration is continuous at t equals 0. Okay. So of course, if we want to work with the acceleration, means we have to first find the acceleration. So from the left-hand side, if I consider the function s at t equals 0, well, obviously v at t is just the derivative of that, so that'll still be 0. And a at t, which is just the derivative of the velocity, is still 0. So from the left-hand side, when t is less than 0, nice and easy, acceleration is still equal to 0. Okay. So we're going to work with this function here. So first we'll find the derivative, which of course is my velocity function. Okay, and so here it's just a straightforward quotient rule problem. So here, derivative of the numerator, 3t squared, times the denominator function, t squared plus 1. So notice how, this conversation that I'm having, this might be a good idea if you ever make mistakes with this, is actually say it in your head as you're doing it. Okay, minus the numerator function times the denominator function's derivative, so 2t, okay, all over t squared plus 1, all squared. Okay, now if I was just asking you to find the velocity function, you might want to stop there. But since you have to find the acceleration, it makes a lot more sense to simplify this first. Okay, so let's just do some distribution. So 3t squared times t squared, so we have 3t to the 4th plus 3t squared minus, and that's 2t to the 4th, all over t squared plus 1 squared. And so here we got 3 minus 2, so we're just left with t to the 4th plus 3t squared over t squared plus 1 squared. And I'm not going to bother expanding this, because finding the derivative of this is easy now with the chain rule. Okay, so far so good. We've got the velocity function, which I think we might even need in part B anyways. Okay, but of course we do need it to find the acceleration function, okay, which is just the derivative of the velocity function. Okay, so good thing we simplified this, because now this is again just another quotient rule problem, just a little more complicated. So derivative of the numerator is 4t cubed plus 6t, okay, times the denominator function, which is t squared plus 1 squared, minus the numerator function, t to the 4th plus 3t squared, times the derivative of the denominator. Okay, so now here we got to be careful, because we're going to have to use a chain rule. So this inside here is going to be like my u. So first I take the derivative of u squared, which is 2u, so 2 times t squared plus 1, and then times the derivative of u with respect to t in this case here, so that's just 2t. Okay, all over t squared plus 1 squared. Okay, so let's actually simplify this. This will be a good opportunity to simplify this type of derivative. Okay, and especially since t cubed over t squared plus 1, this is the type of function that we would have worked with very easily in advanced functions. So if we want to still work with these types of functions in calculus, chances are we're going to have to simplify these types of derivatives. Okay, and this, folks, please, please, please do not forget this trick, because it comes in very handy, especially when you're taking these second derivatives here, is I want you to notice in these two terms, okay, because the numerator's got two terms separated by a subtraction, notice that there's a common factor of t squared plus 1. Okay, noticing that is going to make simplifying these types of things much, much easier. Okay, because otherwise you'd have to square this and then multiply it by this binomial. It would be a big mess. So the first thing I want you to notice is that this t squared plus 1, okay, occurs in both terms. Now I'm going to go a little further, because I notice that there's a couple of factors of 2 here, and within 4t cubed plus 6t, you can take out a factor of 2. Okay, so I'm going to take out also this factor of 2. Okay, I'll use square brackets now. So here, consider the factor of 2 I took out, so I'm just left with 2t cubed plus 3t. Okay, here we removed one of the t squared plus 1s, so I still have another one here. Okay, minus, well, this 2 and this t squared plus 1, that all got factored out. Okay, so what I'm left here is I'll put the 2t in front times t to the 4th plus 3t squared. Okay, still not the nicest thing in the world, but a heck of a lot nicer than had I not factored out the t squared plus 1. Okay, and here I just noticed I made a little mistake here because it's the denominator squared. So since it was already squared, this should be exponent 4. Okay, so another little trick to keep in mind, okay, that I've suggested to a lot of people is when you're doing stuff with a lot of algebra, always take a look at the previous step quickly before you move on. Okay, so here I noticed that I forgot to square that denominator. Okay, another nice thing here, I see I got a t squared plus 1, and I can eliminate that with one of the t squared plus 1s in the denominator. Okay, so let's keep going. So I got this 2 in front. So here I'm going to have to, distribute this. So this is 2t to the 5th, okay, plus 2t cubed, okay, plus 3t cubed, plus 3t. And here I've got minus 2t to the 5th, so that's quite nice, and then minus 6t cubed. Okay, and don't forget here it's t squared plus 1 cubed now. Okay, and that works out pretty nicely because the t to the 5ths cancel out. Okay, so here we're left with 2t cubed plus 3t cubed, that's 5t cubed, minus 6t cubed, so I'm left with negative t cubed, and the only thing left over is the plus 3t. Okay, and so what we have here is a fairly simple function for our second derivative or acceleration function. Okay, but let's remember what we were actually asked to show. We were asked to show that our acceleration function is continuous at 0. Okay, so this only represents, okay, so if we were to write the acceleration function, okay, remember that this is only valid, okay, so 2 times negative t cubed plus 3t all over t squared plus 1 to the 3 is valid for t greater than or equal to 0. But don't forget that if we go back up here, the second derivative of 0 is just 0. So this is equal to 0 for t less than 0. So if we want to determine whether this is continuous, we need to show that the limits are the same for both sides. So here, limit as t approaches 0 from the left of a at t. Okay, well that's just equal to 0 because a of t is just equal to 0 there from the left. Okay, and if I take the limit as t approaches 0 from the right, okay, excuse me, that's just the limit of this thing here of 2 times negative t cubed plus 3t over t squared plus 1 cubed. Okay, and since 0 does not make the denominator equal to 0, I can just input 0 here, and I notice I've got 0 plus 0 is 0, so the whole thing is equal to 0. So these are equal, so we have continuity. Okay, now let's take a look at part B. Okay, and that asks us to, what happens to the velocity and acceleration for very large values of t. So in other words, what they're asking us to find is the limits at infinity. Okay, now here for very large, so we're only interested in t approaching positive infinity of the velocity function. So I'm not going to actually, excuse me again, write it out. So let's look at our velocity function, which was this here. And you notice that I have a 4th degree polynomial in the numerator, and if I were to expand this out, I'd get a 4th degree polynomial in the denominator. So there's going to be a horizontal asymptote, so I just have to look at the quotient of the leading coefficient. So here the leading coefficient is 1. If I were to expand this out, the leading coefficient would also be 1. So that means that the velocity is approaching 1. And here, do they give us any, well, they don't give us any units. So it's 1 unit of distance per unit of time. Okay. Then they ask us what happens to velocity function for very large values at t. So they're looking for the end behavior, or the limit at infinity of the acceleration function, and let's take a look at that one there. And if we look at the acceleration function, we see that we have a cubic in the numerator, and this is going to be a 6th degree polynomial in the denominator. So since the degree of the denominator is larger, we know that its end behavior will just be 0. So this is distance unit per time units squared. Okay, like meters per second squared. Okay, so velocity is approaching 1, and the acceleration is approaching 0. Now if you think about it, that makes sense, because if you've got the velocity function that's approaching a horizontal asymptote, it makes sense that the slopes of the tangents are flattening out. So not a surprising result. Okay, so notice here how important it is for your algebra to be tip-top shape, because there is quite a bit of work in just finding the second derivative for this fairly simple function. Okay, that's it for this one.